today. This weekend, Cam asked me, Daddy, did you have electricity in cars when you were growing up? And so I'm just curious a little bit as to, do you remember a time before email? Do you remember a time before cell phones? Okay, so the 10 o'clock also remembered, life before cell phones. The only reason my kids know what, original telephones look like is from Toy Story 3, because they have the Fisher-Price phone character. And so we actually then picked up that over a few years ago at a garage sale. Okay. So today, usually you guys are actually have an advantage over the 10 o'clock in that by the time I give the lecture, I've worked out some of the kinks. But with the flu that I'm battling, it's actually harder for me to stay upright this long. So you'll get a sense of what the 10 o'clock goes through. Today we're going to be doing optimization, which is one of the whole purposes of multivariable calculus. So again, we had the exam question where I was asking you, what the hell was the point of Calc 1, Calc 2? You should know why you're taking a class. One of the reasons we develop all this theory of multivariable calculus is we want to be able to solve problems. We want to optimize things. And so I'm going to start off with one of my favorite examples of optimization. So before I do that, as always, hand in homework, grab old stuff, grab solution keys, and the first quiz is finally available. The quizzes are diagnostic. I will calculate your average on them. If it helps your average for the course, I will incorporate the quiz average into your grade. If it doesn't help your average for the course, I won't. I really want you to use these quizzes as a chance each week to get a sense of how well you're doing. Don't look at the quiz until you're ready. Try to do it in 10 minutes. It's closed book. The purpose is to get a sense of how well you're understanding the material. Anybody familiar with the Battle of Trafalgar? One of the greatest and most lopsided military victories of all time. Of course, since this involved the French, that's not so surprising. It was a British fleet under the command of Horatio Nelson, not surprisingly on HMS Victory. He had around 27 ships of the line, I think, fighting 32 Allied Spanish and French ships. Conventional military strategy at the time was for the two fleets to basically go sideways so that they could unleash their salvos and fire their guns at each other. Nelson had a new idea. He took his fleet and drove a wedge into the French and Spanish lines. And what he wanted to do was the French and Spanish had more ships. He wanted to divide them into two groups and have most of his ships fighting a large contingent of French-Spanish ships and a small amount of his force basically doing a delaying action against the Spanish-French and holding them off until his main fleet had finished the group they were fighting against and then could swing back and help the smaller group. This was contrary to naval strategy at the time. The question is, what is the best way to split your fleet and what's the best way to split the enemy fleet? This actually is a really nice calculation in differential equations. It's a really nice optimization problem. If you're interested, I've posted some Mathematica code and I've posted some articles on how you actually find the optimal value. Not surprisingly, based on the outcome of the battle, Nelson was very close to the mathematical optimal of what to do. The French-Spanish lost, I think, 22 out of 32 ships. The British lost 0. It was a major victory for the British. It solidified their command of the seas. It helped cement all the jokes you now hear about French military forces for centuries to come. Obviously, there were no cameras back then to record the battle, so these are computer simulations as to what people thought it was like. There's another clip that does a better job of actually showing the deployment of the forces, which I think is, it's about an 8-minute clip, but it's really worth looking at when you think about the applications of mathematics. Mathematics in warfare is huge. And these are extremely important optimization problems. Trying to figure out how to deal with stuff like this has been huge in terms of developing the general theory. As a side note, to make sure no one's feelings were hurt, for the 100th anniversary of the Battle of Trafalgar, when they reenacted it, they had it as red versus blue. So nobody would feel bad. Okay, so what I want to do today is I want to talk about optimization. So as always, we have to start with a bit of notation. We say f has a global or absolute max at x naught if for all x in the region, f of x naught is greater than or equal to f of x. So there can be other points that are equally large, but no point is larger. And of course, we have a similar definition for a global or absolute minimum. Similarly, we have a local. We say f has a local max at x naught if for all x close to x naught, we have f of x naught greater than or equal to f of x. So of course the question is, well, what do we mean by close? This is where that topology notation, the open sets that we talked about before, come into play. So typically what you would mean is I give you a point, I draw a small circle if I'm in 2 dimensions, or a small ball if I'm in 3 dimensions, and I say I just look at points in that small ball. And as long as I stay in that small ball, I can't find anything larger than my f of x naught. And so, using my wonderful artistic abilities, if I give you something like this, this is going to be the global max. This would be the global min. We would have local max at here and here. We would have a local max here. There is one more local max. Or actually 2 more potentially. Where's the other local max? Good, so here's a local max. And there's one other. The global, right? If you're the best, you're also the best locally. Okay? So this is the definition of local and global. And the question is, how do we find these? So there's a wonderful result. So this is the key result from analysis. So let f be continuous on a closed bounded region. Then f attains its max and minimum on the region. So I'm not really going to specify what closed means. The technical definition is a set is closed if its complement is open. For us, think of closed as an open set that includes its boundary. So if you want, think of a ball, think of an ellipse, something like that. One of the best things that ever happened to me when I was an undergraduate in math was one of my professors told me, whenever you have a theorem, remove a condition. The theorem should either be much harder to prove or false. And so let's remove the conditions one at a time and see what happens. If f is not continuous, well, consider a function like this. This function has no global maximum. As I get closer and closer to this point, my function is constantly getting larger and larger and larger. It never reaches its maximum. Similarly, it never reaches its minimum. So no maximum or minimum. The next one is endpoints. So consider an open interval. And so here's 0, here's 1. You might remember functions like this from trig. So as I get closer and closer to 0, I'm going to plus infinity. As I get closer and closer to 1, I'm going to minus infinity. This function has no max. It has no minimum. It's very important that I have my region be closed. And the last was bounded. If region is unbounded, so imagine I have something like this. I'm getting closer and closer to 1 as I get up to plus infinity. And I'm getting closer and closer to minus 1 as I go off to negative infinity. And so again, I don't have a maximum or minimum. So it's very important to get a sense of when you expect a maximum or minimum to exist. Well, it's not surprising that a function needs to be continuous. If a function is discontinuous, anything can be happening. It could be about to reach that maximum value, and I've just instantaneously been transported someplace else. The other conditions are a little bit more subtle. But, all right. So this is the notation. This is the key result. If you take a course in mathematical analysis, you would prove a result like this. All right. So before we do anything in several variables, what do we always do? I'm sorry? Do it in one. Right? So let's go back and let's review Calc 1. So in Calc 1, you found maxima and minima. So how did you find maxima and minima in Calc 1? Okay, and then in what? Okay. In one dimension, take first derivative, set equal to 0 to get critical points. These are the candidates. All right. What I want you to do is I want you to tell me at what moment in time you think I am traveling at my fastest speed. Okay? I'm going to just run towards the door. I am so glad I only teach this class twice. All right. I'm not going to do this again. There will be eventually a video posted. You can look at that as many times as you want. Do not put it on YouTube. Someone could have gotten so many extra credit points if they had answered this problem fully. What did you all miss? Endpoints. Don't ever do this again. Right? You need to check the endpoints. It's not enough to just check the critical points. I really hope that this will drive home the lesson. Actually, I should have brought my kids to school. Kim would have had fun doing that. I would have done that again and again and again. So let's talk about why we missed the critical points not being sufficient, why we forgot the endpoints. Let's go back to the definition of the derivative. So f prime of x naught is the limit as h tends to 0, f of x naught plus h minus f of x naught divided by h. So here's x naught. Let's assume f prime of x naught is greater than 0. Case 1, h is greater than 0. Well, if the denominator is positive and the limit is positive, what do you know about the numerator? Positive. So the numerator is greater than 0. Thus, f of x naught plus h minus f of x naught is greater than 0. So f of x naught plus h is greater than f of x naught. Therefore, f is increasing to the right. So I don't know exactly what my function looks like, but I know as I go a little bit to the right, my function has to be getting larger. Let's look at what happens if the first derivative is positive. So same case, assume f prime of x naught is greater than 0. But now, case 2, assume h is less than 0. So we've traveled a little bit to the left. We've moved backwards. So now, in this case, the numerator is less than 0. Thus, f of x naught plus h minus f of x naught is less than 0. This means f of x naught is greater than f of x naught plus h. So f is decreasing to the left. And so now we can really mine this to understand what's going on. What we've just seen is if the first derivative is positive at a point, this point can't be a maximum. Why? Just go a little bit more to the left. I'm sorry, go a little bit more to the right. Let time pass a little bit more. Your function's getting larger. Your speed is positive. It can't be a minimum. Why? Go back in time a little bit. So you can't be at a maximum or minimum if your first derivative is positive. Similarly, you can't be at a maximum or minimum if your first derivative is negative. So there's only one case left. The first derivative must be 0. This gives you the candidate points. And so there's a big difference in English between the words, or at least in mathematics, between the words necessary and sufficient. It is necessary that the first derivative is 0. That doesn't mean it's sufficient. But if the first derivative is not 0, we can't be at a maximum or minimum. Unless what? Unless it's an endpoint. So for example, if this is my function, and here's a and here's b, my first derivative is positive. I want to keep going further. I'm not allowed to. I'm only looking up to b. Think of it as the hard door over there that you cannot pass. Okay? So it's actually useful that they're making all that noise outside, and we have to have the door closed in this class. Okay? Don't forget the endpoints. All of our analysis of what's going on is here, assuming we're not at an endpoint, assuming we're allowed to go further. We can't be at a maximum because if we move a little bit more to the right, we'll be larger. Well, at the endpoint, we can't move any further to the right. Okay, so again, this is the key point to remember. In one dimension, how bad is it to take care of the endpoints? How many endpoints are we talking about? 2, okay? In the scheme of life, asking you to check 2 endpoints is not that much. Now in multivariable calculus, imagine you have a function defined on a circle, on a disk. How many endpoints are there now? Infinitely many. The theory is now a lot worse. And we need a good way to check infinitely many points. We do not want to check infinitely many points by hand. We can't. We have to find a good, efficient way to do that. This is the method of Lagrange multipliers. How many of you are econ, potential econ? Not quite as much as 10. But we will talk about applications of this when we get to Lagrange multipliers. So we will deal with how do you handle constrained maximum minimum. It's one of the most important topics in multivariable calculus. As an aside, how many of you have seen Family Feud? All right, we will be doing Family Feud on Wednesday, 10 o'clock versus 11 o'clock. Winning class gets homework exemptions. Okay? So either come to your section and do a good job or go to the other section and sabotage. You have a choice. So it's really important right now that you know who is in your class. And so if you see somebody who is not normally in your section saying bad things, okay. So this is the theory in one dimension. Now that we've mastered the theory in one dimension, the question is how does it generalize to several variables? And again, we're not going to deal with the boundary first. So higher dimension. To find candidates in the interior to be maximum or minimum, find the critical points. i.e. x, such that the derivative of f, which is the gradient of f, which is the grad of f, or in full glory, df dx1, df dxn is 0. And that's the 0 vector, not the 0 number. So this is the correct generalization of critical points. If you think about going down to just one variable, then that's just df dx or f prime equals 0. That's the regular critical point. What I'm saying here is I want all of my partials to vanish. So the proof is essentially repeated applications of Calc 1. So proof, apply Calc 1 n times. So imagine I'm at some point here, and I want to be at a local maximum. If df dx1 is positive, well, my function's increasing if I go to the right. I can't be at a maximum. I'm decreasing if I go to the left. I can't be at a minimum. So the only way I can have a chance of being at a maximum or minimum is if df dx1 is 0. Similarly, if I look at what happens if I move in the y direction, if df dy is positive, I increase going this way, or I decrease going this way. And so we can just argue component by component by component. And so the only way we can possibly have a maximum or minimum is if the gradient is the 0 vector. This does not mean we are actually at a maximum or minimum. This just means we have a candidate. It's very important to remember the difference between candidate. In Calc 1, how would you tell if you have a maximum or minimum? So there were two ways you were taught in Calc 1. How do you tell if you have a maximum or minimum? What tests did you learn? Take the second derivative. So in one dimension, we have the second derivative test. If the second derivative is positive, you have a minimum. If the second derivative is negative, you have a maximum. I never remember the second derivative test. I always just rederive it on the spot. I'm going to show you how to quickly rederive the second derivative test, assuming you can remember one thing, that there is a second derivative test. So as long as you remember that the sign of the second derivative tells you if you have a maximum or minimum, I'll show you how to remember which way. Consider f of x is x squared, and g of x is negative x squared. Then f prime of x is 2x, f double prime of x is 2, and my function looks like this. I have a minimum. G prime of x is negative 2x, g double prime of x is negative 2. My function looks like this. I have a maximum. So as long as you remember roughly the shape of the second derivative test, if you check it out with some special functions where you can just quickly stare at them and say max or minimum, then you can remember what the second derivative test is. There's also the first derivative test, which I won't go over right now, but it's extremely important. The following is almost surely an apocryphal story, but it's funny. It illustrates a good point about the need to check to find if you have a maximum or minimum. The story goes, years ago, there were people who were working on the very first stealth bomber, stealth fighter. What was their goal? So you're building the stealth bomber, stealth fighter. What's your goal? Not be seen. You want to minimize visibility. The way the story goes is they didn't check to see if they had a maximum or a minimum, and technically they built the I'm here plane. Almost surely not a true story. But it's funny to think about very smart people forgetting to do something very simple and just checking at the end of the day, do we have a maximum or minimum? And accidentally building the most visible of all possible planes. Okay? Almost surely didn't happen, but it's a good way to remember the need to check something like this. The second derivative test is far more complicated in several variables than it is in one variable. And we'll talk a little bit about it later, but it really makes much more sense after you've taken linear algebra, of course, right? Everything becomes so much nicer after you have linear algebra and the language of that to handle these issues. Okay, So we do have, at least in one variable, a way to determine if we have a maximum or a minimum. And we understand the need. Now, there are a lot of problems where it's clear from physical grounds if you have a maximum or a minimum. Frequently, if you have some surface and you want to find the point closest to the origin, if the surface is going off to infinity, there's going to be no point a maximum distance away. You can always get a point further away. So whatever you find will be a minimum. So there are a lot of times from physical reasons you're finding a minimum or maximum. As an aside, if you're ever told to minimize the distance, never do that. Never minimize distance. Instead of minimizing distance, what should you minimize? Distance squared. Distance involves the square root. You don't want to do calculus and take derivatives involving the square root. If you can minimize the distance squared, that's the same as minimizing the distance. Okay, so this is the review of one dimension. We've seen in several variables that we want to look for the place where the gradient is 0. So what we're going to do now is we're going to look at some examples. These examples are, of course, completely make-up examples. They don't matter. These are functions that are not important. The goal of these examples is to highlight the methods and the techniques. Sadly, what you will find is most of your time in a calculus class, you will not be doing calculus. What will you be doing? I'm sorry? Algebra. Most of your time will be spent doing algebra. I have been doing these problems probably as long as you've been alive. I think I finally reached that point. After doing problems this long, one, they do get boring, yes, but you do find good ways of looking at the algebra and finding fast ways through it. Don't be afraid to just hack through it. If you can see the right way or a cleaner way to do the algebra, you'll save yourself some trouble. You'll minimize the chance of making an error. Don't worry if you don't see them, just hack away at it. The difficulty is when we do all this stuff, we have to then solve for this vector equals 0. And in general, that's going to give us a hard system of equations to work with. All right. If I give you a homework problem, if I give you an exam problem, what do you know about the algebra? It's at worst medium. Probably though on the somewhere between easy and medium. It's not going to be hard. It's not going to be undoable. In the real world, you almost surely would have to resort to a computer. If I'm giving it to you on homework or on an exam, it's got to be something you can do. So you do have that advantage when you're doing these problems. These are not real world problems. So the algebra will be somewhat doable. So the first one is the extremely pleasant example where I tell you f of xy is x squared plus y squared minus 6x plus 2y plus 5. And I'm trying to just use the same examples that are in my lecture notes. And I want to find the critical points, and I want to find the candidates for the maximum and minima. So df dx is going to be 2x minus 6. df dy is going to be 2y plus 2. So critical points are where df dx and df dy are 0. All right? So critical points, we have 2x minus 6 equals 0, and we have 2y plus 2 equals 0. Using my years of algebra experience, I am able to go from here to x equals 3 and y equals minus 1. Right? This one here is, of course, ridiculously easy because one equation only involves x, one equation only involves y. This is not the typical case. But we get the solution. The solution is the point 3, 1. OK. Any questions on this example?
Why is it 1 and not negative?
Oh, because I can't copy correctly. OK. Yes?
Is it the solutions meaning the critical points?
So this is the critical points. So we were trying to find the critical points. Here's the critical point. So now my question is, do you think we found a maximum or minimum? And how can you determine whether or not it's a maximum or minimum? So I haven't given you the several variable second derivative test. So don't say use the several variable second derivative test. That's not available right now. How can you tell if you have a maximum or minimum? What can you do to try to get some information? I'm sorry?
Plug in 0, 0 into the original function and then see if it's greater or less than that.
That's not horrible, but 0, 0 is kind of far from here. So instead of doing 0, 0, what should you do?
Points on either side.
Points very close. So try maybe 2.9, negative 1.1. Try some points very close by. And so, your idea of using 0, 0 is good. It's just 0, 0 is so far away that you could be mistaken. But if you try a couple points that are really close, if you always find something that's smaller or always find something that's larger, then you're beginning to get a sense. Do you think that this is going to have a maximum or a minimum? Well, if you look at the function, what happens to this function as x and y get large? Yeah, you've got this x squared plus y squared, which is going to kill the negative 6x and the 2y. So just by looking at this function, my intuition tells me we should be getting a minimum. The other thing you can do is you could apply the second derivative test in just one variable, is keep y fixed, and then just look at this as a function of x when y equals negative 1 at the point x equals 3. And this is not going to be perfect because you can move in more than just two directions, but it will give you some intuition. And if you do this in both of those directions, you'll see the second derivative tests in the x direction, the second derivative test in the y direction, both give minima. So even when you don't know the full way how to attack this problem, you can still glean a lot just by looking at it. And again, this is one of the skills I want you to get out of this class, is it's wonderful to be able to crunch through and apply powerful machinery to a problem, but most of the time you're going to have equations that are far too complicated to solve exactly. You want to look at the equation and get a rough sense of what it's saying. Well, x squared plus y squared is becoming so large, I think roughly it looks kind of like this. And so I'm expecting I'm going to get a minimum. Okay, any questions about this beautiful function? We can consign it to the dustbin? Okay, goodbye. All right, so now we're going to go to a more interesting example where the algebra is a little bit more fun. And so the example now is going to be the following. We're going to have f of xy is x squared y plus 3xy squared. And so, arguing as before, we get df dx is 2xy plus 3y squared. We get df dy is x squared plus 6xy. And critical points are where df dx equals df dy equals 0. We have sadly finished the entire calculus part of this problem. From this point on, it's now an algebra problem. Okay? So the critical points, we have the following. We have 2xy plus 3y squared equals 0. And we have x squared plus 6xy equals 0. There's a lot of ways to do the algebra for this problem. One way is I could try to solve for x in terms of y. So use one equation to eliminate one variable, plug that into another. Anybody see another way? Yes? So I could set them equal to each other. That's not going to be too helpful, unfortunately. But if I were to tweak one of them and then set them equal to each other, that would help. What should I multiply one of them by? Yeah, if I multiply the top by 3 and subtract, then the 6xy terms will cancel. What else could we do? What would you love to do to the second line? Factor. So you could factor it as x times x plus 6y. You can't just cancel the x. Why can't you cancel the x? I mean, x multiplies the left-hand side, so why not just divide both sides by x? I'm sorry? You lose a solution. Which solution do you lose? Well, if we pull out an x and we have x times x plus 6y equals 0, we lose x equals 0. Oh, wait a minute. If we're losing x equals 0, if we divide by x, what have we just done? We've just divided by 0. So if you factor this, it's fine to factor and then say either x equals 0 or x plus 6y equals 0. You can't just factor out the x and cancel it, because you could divide by 0. So you've got to be very careful. One way I like to do this problem is to say, hey, look, I've got an xy here, I've got an xy here. This is the same as the following. I can write this as xy equals 3 halves minus 3 halves y squared. And I can write it as xy equals minus 1/6 x squared. So it's perfectly fine to do it this way. Again, all of these different algebra approaches are fine. I just want to discuss a couple with you and then just show you one. Well, now I get negative 1/6 x squared equals negative 3 halves y squared. So I get 1/6 x squared is 3 halves y squared, or I get x squared is 9y squared. So what are my solutions? X is so if x squared is 9y squared, x is plus or minus, right? Very important to remember the plus or minus. Right? There's two possible solutions. Okay? So again, it's not the calculus that people are most likely to make mistakes at here. It's the algebra. So case 1, let's say x equals 3y. So how would I finish solving this? I now know x equals 3y. What can I do to figure out exactly what value x and y take on? Yes? Excellent. We have two equations here. So I can substitute x equals 3y back into one of these equations. Which should we substitute into, the top or the bottom? Top. Here we have x occurring in two places. Here we have x occurring in one place. Does it matter? No. But it will make my life easier. Okay. So we now get 2 times 3y times y plus 3y squared equals 0. So we get 6y squared plus 3y squared equals 0. 9y squared equals 0. Okay, so y is 0. I'm not going to write plus or minus 0. Okay, so in that case, we found the solution. The second case, x equals negative 3y. Oh, it's very similar. We get 2 times negative 3y plus 3y squared equals 0. So we'll have negative 6 times y. We'll get negative 6y squared plus 3y squared. So we get minus 3y squared equals 0. Therefore, again, y equals 0. So in both cases, we get y equals 0 is the only solution. And if y equals 0, what does x equal? Yeah. In this case, x is equal to plus 0. In this case, x is minus 0. Same thing. So only solution is 0, 0. So that's our candidate. Okay. Yes?
Why do we have to go over this and not instead say that since we have the squares in both cases, either of them has to be 0? Otherwise, the equation wouldn't be equal to that. The critical points. Probably.
In which one?
The critical points. Probably.
Right here?
Yeah, since we have the squares, why don't we from the beginning say that x or y in each respective equation has to be 0?
Well, what if this is a negative number here? See, x could be positive, y could be positive, I'm sorry, x could be positive, y could be negative, and this could cancel with that. If I just had 3y squared, then absolutely I could immediately conclude that y had to be 0. But because I have that 2xy, now the other thing is we could factor, we could say either x equals 0 or x plus 6y equals 0. And we could factor here and say either y equals 0 or 2x plus 3y equals 0. And you'll check that in the other and see, oh wait, those two ones are not mutually compatible. So the only things that will work is when they're both 0. There's lots of ways of doing the algebra here. Okay, any other questions about this problem? All right, so continuing the Cam Kaler theme of things from childhood, how many of you have ever read the story Click Clack Moo? How's that type? So it starts off with Farmer Brown has a problem. In the children's story, it says cows are typing and the typing is bothering him. But in a Calc 1 class, you might have met Farmer Brown. He is obsessed with rectangular pens, and he will not consider fencing his cows in anything but a rectangular pen. And depending on how well the economy is doing, he has either 40 meters or 100 meters of fence, and he wants to find out what's the maximum pen he can create in a rectangular shape, largest possible area, given the amount of fencing he has. And you solved this problem hopefully in Calc 1. You may have met Farmer Brown's brother or cousin, Farmer Bob. Farmer Brown and Farmer Bob both love rectangles, but Farmer Brown lives by the river. And so he has, or a mountain, depending on which book you have, and he has this river or mountain which gives him one side free that he doesn't have to fence. And he only has to put down 3 sides for his rectangular pen. And there's a really nice way to quickly solve Farmer Bob if you know Farmer Brown by doing a reflection. So if you've seen this problem before, it should be a little bit surprising to be doing this problem in a Calc 1 class because it involves 2 variables. But you were able to solve this in a Calc 1 problem, in a Calc 1 class. How are you able to do this function of 2 variables and optimize it when in Calc 1 you only knew how to optimize things in 1 variable? What did you do? You translate it into a function that only has 1 variable. You use the fact that we have this perimeter relation, 2x plus 2y equals 40, to then solve for y in terms of x, and then the area function becomes just a function of x. We're going to do the same thing right now for a box problem. And again, we're lucky that we're in a situation where we can quickly incorporate the constraint. But the goal is not to do this. The goal is eventually to get to Lagrange multipliers and see how you would handle the more general case. And we want to be able to deal with these constraints. In some cases, we're lucky enough that we can very easily solve for 1 variable in terms of the others and basically remove the constraint and absorb it by having a new problem to look at. So the problem we have here is we have a box must be 48 cubic feet. Yes, they're using the English system. Right? We want to have 48 cubic feet. So the box looks something like this. Let's say this is x, this is y, this is z. And we know the top and the bottom cost $1 per square foot. The sides cost $2 per square foot, and the ends cost $3 per square foot. I may mix up a little bit which is x, y, and z from what I have in my notes. I may mix up exactly what is the front, what is the side. Doesn't really matter. What's the volume of the box in terms of x, y, z? X, y, z, yep. Volume is x, y, z, and that must be 48. And the cost, so I have $1 for the top and the bottom. All right, so the bottom is x times y, so the area of the bottom is xy. I have xy in the top as well, so it's 1 times 2xy. Now I need the sides. The sides will be z times y. I have 2 of them again. Each one costs $2. 2 times 2 zy. And then last is I have the ends, which is going to be x times z, and those will be $3 each, and I have 2 of them. So I would love to maximize minimize this function, but unfortunately it involves 3 variables and there's a constraint. So the question is, what's the best way to go about this? Well, we somehow have to eliminate a variable. What variable should we eliminate? What variable should we eliminate? Z. Absolutely, it's the last letter in the alphabet. Right? We're much more common, much more used to using x's and y's. Z always goes first. So z is equal to 48 over xy. And so we get a new cost function as just a function of x and y. It's going to be 2xy plus 2 times 2 is 4. Z is going to be 48 over xy. The y's cancel. I get 4 times 48 over x. And the last is I'm going to have 6 times 48. The x's cancel, and I'll have over y. All right. dc dx is going to be 2y minus 4 times 48 over x squared. dc dy is going to be 2x minus 6 times 48 over y squared. And what do I do to find the critical points? I set them equal to 0. So critical points. dc dx equals dc dy equals 0. So we get 2y minus 4 times 48 over x squared is 0, and 2x minus 6 times 48 over y squared equals 0. And we're now done with calculus. All right? Now this is back to algebra. So the question is, what's the best way to handle this? So I could solve for y in terms of x, substitute that into the second equation, and start playing around. One thing I like to do is I like to try to find commonalities. I like to try to find common patterns. I almost have the same thing here. This is a 2y, this is a 2x. If I multiply this by x and this by y, I have the same expression. And that trick led to clean algebra in the previous problem. So if I just multiply both sides by x and move things over, this becomes 2xy equals 4 times 48 over x. 2xy equals 6 times 48 over y. And now what can we figure out? So now if 2xy equals this and 2xy equals that, we get 4 times 48 over x equals 6 times 48 over y. Yes. And now there's actually something worth noting here. And I also did this in the 10 a.m. section. I'm lazy. That's one of the things you should strive for as a mathematician. Don't do calculations needlessly. I didn't want to do difficult multiplication like 6 times 48. My hope was that that might actually cancel out later, and it actually does over here. I don't have to worry about that. I get 4y equals 6x, or equivalently, 2y equals 3x. So now all I have to do is substitute this into one of the equations and solve. Should I substitute into the first equation or the second equation? Yes, why?
Because you have 2 y's, you don't.
Yes, I don't have to do any algebra. There's no need to even solve for y as 3/2 x. You know, we're fortunate. It's screaming at us. I've got a 2y here, you've got a 2y here. Everything matches perfectly. We substitute. And we get 3x minus 4 times 48 over x squared equals 0. 3x cubed equals 4 times 48. 3 goes into 48 how many times? 16. You can almost guess it has to be 16 because we have an x cubed. We need to have a perfect cube on this side because this is a cookbook problem from the book. So the answer almost surely is going to be nice. So almost surely it's either going to be 4 times 2 or 4 times 16, so that we're going to have a nice cube root. And so we end up getting x equals 4, because this is the same as 4 cubed. All right, well, if x equals 4, what does that tell us about y? So if x equals 4, well, 2y equals 3x. 2y is 12, so y is 6. And now what is z? It's going to multiply out to 48. 4 times 6 is 24, so z has to be 2. So I'll admit I'm bored at this point. Actually, I was probably over there, but once we get to this point, there's no mystery anymore, right? Once I know x equals 4, I have a relation that tells me what y is given x. I can now find y. Once I know x and y, I have z as a function of x and y. And I can just pick them off one at a time. So again, there's not one right way to do the algebra for these problems. This is either good or bad depending on your point of view. Whichever way you're more comfortable with, by all means, feel free to do. There's lots of different ways to get to the right answer. Don't be afraid to try something, work with it for a while, and if the algebra is becoming nightmarish, put it off to the side and take a new piece of paper. And just try another approach to it. The amount of calculus that we need to do is minimal. Once we've taken the partial derivatives, we're done. Then it's just dealing with the algebra to try to find the solutions. Okay. Any questions on this problem? So one of the nice things is now that we've gone through a lot of the material in the beginning of the semester, we can be a little bit more leisurely, not too much more, but a little bit more leisurely for the rest of the semester. Again, it's a real rush to get all the material in, but we're in pretty good shape right now in terms of where we are. All right, so the quiz is due at the start of class on Wednesday. There is no partial credit. You should view it as more diagnostic than anything else. This is to just get a sense of how you're doing with the material. New homework is on the bottom of the solution key, and then old homework is here to be picked up.